Hi everyone, I'm Alex Wein, and this talk will be based on joint work with David Gamarnik, Akos Jagannath, and Schramm. I'll be talking in broad generality about problems in high-dimensional statistics. A motivating example is that of finding a large clique in a random graph, like the one shown in red. There are a few different variations of this problem. In detection, I give you a graph that's either a random graph or a graph with a planted clique, and your job is to decide which it is. In recovery, I give you a graph with a planted clique, and your job is to find the clique. And in optimization, I give you a random graph with no planted clique, and your job is to find as large a clique as possible. Problems of this flavor often have a gap between what is possible information theoretically and what is possible with a polynomial time algorithm. For instance, in the planted clique problem, it's possible to detect a clique as soon as its size exceeds 2 log n, but we only know a polynomial time algorithm to detect a much larger clique of size roughly square root of n. We would like to understand what fundamentally makes problems easy versus hard, and amass concrete evidence for why no algorithm should exist in the conjectured hard regime. There are various frameworks for understanding computational complexity of statistical problems, but I will focus on just one called the low-degree polynomial method. This originated from a line of work on the sum of squares hierarchy by all of these authors listed here. The idea is to study a restricted class of algorithms, namely low-degree polynomials. Here I mean a multivariate polynomial that takes in the entire observed data as input and outputs a solution to the problem, which could either be a scalar or vector depending on context. When I say low degree, it means logarithmic in the dimension. It turns out many of the best algorithms can be represented as low degree polynomials. This includes spectral methods and AMP-style algorithms. For many of the natural problems arising in high-dimensional statistics, it has been demonstrated that the class of low-degree algorithms is as powerful as the best-known polynomial time algorithms. This talk will be about techniques for proving that all low-degree polynomials fail to solve a given task. If we are able to prove such a thing, this constitutes evidence that the problem is fundamentally hard. I'll talk about a few different settings. For context, I will first tell you about some prior work on the detection setting, and then I will tell you about some new results that extend the framework to recovery and optimization. Okay, so let's talk about the detection problem, where the goal is to hypothesis test between two different distributions. The first is the null model, for instance, an Erdős-Rényi random graph, and the second is the planted model, for instance, an Erdős-Rényi random graph with a planted clique. We'd like to understand whether there is a degree D polynomial that can distinguish these two in the following sense. F takes in the entire graph as input, represented as an adjacency matrix, and it outputs a single number. To succeed, this number should be big if the graph came from the planted model and small if it came from the null. More formally, we'd like to understand this quantity, the maximum over all degree D polynomials of the mean value in P divided by the fluctuations in Q. If this value tends to infinity as the dimension goes to infinity, we say that degree D polynomials succeed, and if it remains bounded, we say that degree D polynomials fail. This quantity may look difficult to control, but we'll see that it's actually a simple matter of linear algebra. To see this, we should define an inner product on functions with respect to Q, as well as the associated norm. And we'd like to write everything in terms of this notation. First, we need to change measure in the numerator from P to Q, and we can do this by throwing in a factor of the likelihood ratio. Then we can write everything in terms of the norm and inner product. And now notice that the degree D polynomials form a subspace. And so we can think of F as a vector constrained to a subspace. And now it should be clear that the optimal F is just the orthogonal projection of L onto the degree D subspace. So this gives us an explicit characterization for this value called the norm of the low degree likelihood ratio. In order to actually carry out this projection step, we need to expand L in a basis of orthogonal polynomials with respect to Q. And typically such a basis can be found if Q has independent entries. Okay, now let's switch gears to recovery. So for some problems, we know that recovery and detection are equivalent, but in other settings, the recovery problem is strictly harder. One example of this is the planted submatrix problem, where we observe a random Gaussian matrix, where most entries are mean 0, but there's a principal submatrix of elevated mean lambda. The goal is to take this matrix and estimate V, which is the indicator vector for the planted coordinates, but by symmetry, we can just think about estimating the first entry, V1. A natural quantity to look at is the best possible mean squared error achievable by any degree D polynomial. But it will be more technically convenient to work with an equivalent characterization called the maximum correlation, defined like this. And at the bottom, you can see the simple relation between the mean squared error and correlation. To show failure of all low degree polynomials, we want an upper bound on this correlation. It looks like a similar expression to what we did for detection, so maybe we could try to use the same proof. However, this does not work because we would need orthogonal polynomials for the planted distribution, which seems difficult to come by. We were stuck on this for quite some time, but now we know a simple trick. You can bound the denominator by applying Jensen's inequality, but applied only to the signal part and not the noise. A few lucky things happen after we apply this bound. First, the expression simplifies enough to find a closed form using linear algebra like before. But also, the bounds we get in this way are essentially tight for problems like planted submatrix. Finally, let's talk about the optimization problem. So here, a simple example problem is where I give you a random Gaussian tensor, n by n by n, and the goal is to find a unit vector that maximizes the cubic form. Here, the normalization ensures that the optimum value is some constant, and our result is that no constant degree polynomial can optimize all the way to the optimum value. More formally, here we're imagining a polynomial that takes in the entire tensor and outputs a vector. And in order to succeed, it needs to satisfy two conditions. First is that it needs to achieve a good objective value, but also it needs to be normalized in the sense that the polynomial's output has norm close to 1 with high probability. It turns out that the best known algorithms for this problem fall into the approximate message passing framework, and so actually can be represented as constant degree polynomials. This comes from the work of Subag and Montanari and others. The way we prove failure of low degree polynomials in this setting is quite different from detection and recovery. So the proof has two parts. First, we show that low degree polynomials are stable, meaning that a small random change to the input usually won't change the output by too much. We then establish a variant of the overlap gap property. This is a structural property of the solution space, which roughly says that all the good solutions are separated into clusters. This comes from a line of work started by Gamarnik and Sudan. And it turns out that this variant of the overlap gap property implies failure of any stable algorithm. And that's how we get the result. One open problem here is to improve the value of epsilon. Namely, we would like to show that no low degree polynomial can achieve the precise objective value that is reached by the best known algorithms. All right, that concludes my talk. Thank you for listening. So here are some references if you'd like to know more. Like I said, detection is well studied by prior work, and here's a survey article. And then here are the two papers that extend the framework to recovery and optimization. Thanks.